Welcome to a focused look at the LNG carrier revolution, where engineering meets sustainability. In this presentation, we'll explore how modern design, propulsion, and digital systems are reshaping maritime energy transport, creating vessels that are cleaner, more efficient, and better aligned with global decarbonization goals. And I'll guide you through the key technological innovations and operational shifts driving this transformation. This page shows why change is urgent. Growing global energy demand collides with pressure to decarbonize, and the graphic highlights those twin forces shaping the market. Regulators and customers alike are pushing for lower carbon shipping, while demand for reliable energy transport keeps LNG central, creating a unique convergence that forces rapid innovation across design, operations, and supply chains. Here we unpack the IMO 2030 mandates using the EEXI and CII framework. The slide outlines, and you can see how these measures impose minimum efficiency standards and ongoing carbon intensity ratings. The practical effect is to compel ship owners to adopt cleaner technologies and smarter operations to stay compliant and commercially viable, turning regulation into a hard catalyst for modernization. Modern hull design is no accident. The illustration shows how computational fluid dynamics lets designers fine-tune bulbous bows and stern shapes to cut drag. Paired with advanced lightweight materials, these architectural choices reduce displacement and fuel needs, delivering significant gains in efficiency, lower emissions, and real operational cost savings over a vessel's lifetime. This cross-section compares membrane and spherical tank approaches, and the trade-offs are clear in the image. Membrane tanks maximize usable volume inside the hull, while spherical Moss tanks are self-supporting and robust. Choosing between them affects construction cost, cargo capacity, and route flexibility, so naval architects balance containment performance against operational requirements and safety considerations. The GTT 3-tank concept on this slide illustrates a bold simplification from 4 tanks to 3, preserving nearly the same total capacity while cutting surface area exposed to heat. Fewer tanks means lower boil-off gas rates, simplified construction, and reduced operational complexity, which together translate into tangible cost and efficiency benefits for modern LNG carriers. Managing boil-off gas is a core operational challenge, and the flow diagram shows 3 practical strategies. Superior insulation to reduce heat ingress, onboard reliquefaction to recover vapor, and using BOG as fuel in dual-fuel engines. Each path helps conserve cargo, reduce methane emissions, and give operators flexibility to optimize energy recovery and minimize waste at sea. This slide charts the industry's propulsion shift, moving away from steam toward advanced dual-fuel 2-stroke engines and modern diesel-electric options, as shown by the engine icons. The critical advantage is fuel flexibility, being able to burn LNG or conventional marine fuels, which allows operators to adapt to fuel price swings while meeting tighter emissions standards. The environmental benefits of burning LNG in dual-fuel engines are quantified here with bar charts showing big reductions. SOx and PM fall by over 90%, NOx drops by more than 80%, and CO2 sees roughly a 20 to 25% improvement in many cases. Those gains represent a substantial immediate step toward cleaner shipping and regulatory compliance. Leading engine makers are racing to minimize methane slip, and the slide profiles different technical approaches from MAN, WinGD, and Wärtsilä. Each company pursues distinct gas injection and combustion strategies to reduce unburned methane, and together these competitive innovations are central to lowering greenhouse impact while improving engine efficiency across vessel types. Hybrid propulsion is illustrated here with a schematic showing dual fuel engines, batteries, and electric motors working together. And the practical benefit is clear. Enhanced redundancy, better low-speed efficiency, and the ability to operate engines at optimal loads or shut them down entirely. Hybrid systems are already delivering fuel and emission reductions while paving the way for larger battery capacities in the future. Think of the modern LNG ship as a sentient system, as depicted by the vessel wired to shore-based AI analytics on this slide. Thousands of IoT sensors continuously feed performance and condition data back to predictive maintenance algorithms, enabling crews and shore teams to anticipate failures, optimize operations, and shift maintenance from reactive to proactive for greater reliability and lower costs. Route and fuel planning are becoming data-driven, and the map visualization shows how analytics combine weather currents, vessel performance, and port schedules to recommend the most efficient route. This isn't just shortest distance, it's smart navigation that trims transit time and fuel burn, delivering measurable fuel savings and corresponding greenhouse gas reductions through adaptive operational choices. Autonomy is presented as a staged journey from enhanced decision support to fully autonomous operation, with each phase augmenting human oversight rather than removing it. The current focus is on remote control and automated assistance for navigation and collision avoidance, leveraging sensor fusion and sophisticated algorithms to improve safety, reduce crew workload, and incrementally increase automation. With ships becoming digital fortresses, this slide emphasizes cybersecurity as an operational imperative rather than an option, illustrated by a layered shield graphic. Effective defense mixes network segmentation, continuous threat detection, secure by design software, and crew training, because protecting navigation, propulsion, and cargo systems is essential to prevent disruptions and safeguard high-value maritime energy assets. This economic slide balances CapEx against OpEx and shows why higher initial investment in advanced technologies can lead to lower lifetime operating costs. The life cycle lens often favors early adopters. Fuel flexibility, reduced consumption, and lower maintenance can translate into competitive total cost of ownership and improved appeal to charterers and financiers over time. The human element remains critical as crew roles evolve, and the contrasting artwork highlights the shift from manual gauges to digital control centers. Modern seafarers need specialized technical skills, digital proficiency, and cybersecurity awareness, creating both challenges for training and recruitment and new opportunities for more skilled, engaging maritime careers. Looking to zero carbon fuels, the hydrogen versus ammonia comparison outlines promise and hurdles. Hydrogen can be carbon-free at combustion, but suffers from low volumetric density and costly production, while ammonia stores more energy per volume but raises toxicity and NOx concerns. Both paths require massive investment in bunkering infrastructure before they can scale for deep-sea shipping. The synthesis diagram ties architectural efficiency, propulsion transformation, and digital intelligence together to show how these trajectories create efficiency, compliance, and sustainability gains. Rather than isolated fixes, these interconnected advances form a holistic system that positions the modern LNG carrier as a pivotal convergence point for global energy security and environmental stewardship. In closing, the final slide frames LNG carrier innovation as more than engineering feats. These ships are a bridge to a lower carbon maritime future. The real challenge now is to design transportation systems that serve global energy needs while enabling the transition to zero carbon fuels and smarter operations. And that dual mission will define the next era of sustainable global trade.